You are going to introduce me, right?
Yes, I'm very in Spanish and then I will switch to English, okay? Bueno, les doy la bienvenida al primer ciclo de seminarios de este año 2023 del Centro de Óptica e Información Cuántica, así que muchas gracias por estar acá. Y vamos a partir con una charla en astronomía, ya que justamente Ana nos vino a visitar por parte de un proyecto que se llama Proyectos POEMS, donde ella va a hablar de eso al final de la presentación. Y bueno, este es su último día aquí, así que vamos a aprovechar de dar la charla y los resultados. Okay, so now I'm going to switch to English to introduce Ana. So I'd like to introduce Ana Aret. He did her PhD in the Institute of Physics in the University of Tartu. And then she did some research fellows at the Tartu Observatory. And currently she is the head of the stellar physics department of Tartu Observatory. Her research is about stellar environment of a massive star. Okay.
Yeah.
And the stellar pulsation in massive stars. And today she will talk us about research at the stellar research at the Tartu Observatory. So with that, I would like to present Ana.
Thank you. So first, don't worry, it won't be very much about science, more about who we are, and what we do, what we have, and so on. So it is not necessary to have deep knowledge in astronomy to see that Estonia is here. Well, map of the Europe, we are somewhere between Russia, Finland, and Latvia. And as I said, the Tartu is the second largest city in Estonia. And our observatory is something like 20 kilometers from the city and from the university. So this is on the picture, is the main building of our observatory. And if you see the coordinates, we are pretty far north, so it is 58 latitude in the northern hemisphere. So if you look in the Canada, it is, I think it's probably all frozen at that latitude, but we are warmed up by Gulf Stream. So where we come from, that was like a spatial dimension, in time dimension. Astronomy in Estonia basically started in the beginning of 19th century, when it was observatory, university observatory, built in the hill, on the hill in the center of Tartu. And the interesting thing is that in 1824 we had actually the largest telescope in the world. It was a proud Fraunhofer refractor, and it is still quite alright. It was restored some 10 years ago. But the thing is that if you look at this contemporary picture of this old observatory, it is in the middle of the town, and sometime in the mid-50s, the light pollution from the town became too much. It disturbed astronomical observations. It was not possible, and then it was decided to build an observatory in some area outside of town. So there was a small hill. It's only 72 meters over the sea level, but it is like higher than all the neighborhood, which is almost on the sea level. So this is still a little hill. And there was built an observatory. On top, the picture is before the renovation we had in 10 years ago we had a big renovation, so now we have a very, very modern building, because it was like almost fully destroyed and rebuilt. And for quite a while we were independent observatory, not belonging to any university, and 2018, University of Tartu kind of took us back. So I mean, in the beginning we were observatory belonging to the University of Tartu, and now we again. I think that it is something unexpected happened. Yeah, I wanted to show you. Why does it react? I wanted to show you a drone video. How this is the main building, and there you will see the telescopes. I hope it will load and show. So the main building, and actually everything is there in the main building, like offices, labs, everything. We don't have like a campus, it's one building. And then we see the telescopes. We are now approaching a 60 centimeter size telescope, which is used for photometry. And we have also 30 centimeter small telescope, it's not in the picture. And this is 1.5 meter telescope, which we use for spectroscopy of stars, so stellar spectroscopy, not like galaxies or different supernovae or something. It is for stellar spectroscopy. And actually, in the Northern Europe, it is probably in the Northern Europe it is largest telescope actually. So in this northern latitude, and for astronomical observations, the position of the telescope is actually very important in the sense which part of the sky you can access easily. So who we are? We have 4 departments in our observatory: the stellar physics, physics of galaxies and cosmology, the remote sensing. We are joking that we are all about space. We are looking up, they are looking down on Earth. And also the newest department is the space technology. They are building many nice things, including CubeSats. So now they are about to build the second CubeSat. The first one already, well, it went up and it already disappeared. So this is our group, small group, only 7 researchers. Mostly we are specialized in stellar spectroscopy with the newest addition, Michael Hammer, who is a specialist in planetary formation mainly, and also Hillary, she is running a program for upgrading our telescopes and instrumentation. We are supposed to have a new instrumentation by the end of this year. Also we have students. Vitaly is here and 3 more PhD students. Aini and Vitaly are working in the field of massive stars, and Kertu and Sandipan, they are more studying the host stars or with exoplanets and protoplanetary disks, so another type of stars. Our engineers, of course, and Veronica, our astronomer observer. And actually, Tunovi, who is now counselor, he is a director who hired me when I just graduated from the university. So now I'm his boss. It is kind of a bit strange feeling, but okay. So what we have, you already saw our main building. Everything is there: offices, labs, cafeteria, conference rooms. Just everything in one building. Then we have 3 telescopes. I will just show a little bit in more detail. Maybe it's not so very exciting for physicists, but for astronomers it is a kind of source of big pride. We have our own telescopes, we run them, we use them, and they are far north, so there is no competitors there. Labs were built 10 years ago when there was a big reconstruction, so they do different kind of testing for optical instruments, and some funny tests are for destroying the CubeSats and some components for satellites. So they have a vibration platform and they have a platform for creating some shocks. So they do all the tests to try to, they build a satellite and then they do their best to destroy it. Well, okay. Okay, this is our big telescope as we call it. Also, it is mostly in this smaller telescopes range. We use it for spectroscopy only. We don't have any photometer attached to it. So the spectrograph is a long slit spectrograph. Well, schematically, it is attached to the telescope. So in this picture, you see this spectrograph. It was built in 70s and many times upgraded, updated, and so on and so on. So currently we take spectra with CCD, and this is just example of one blue supergiant star spectrum. It is a single slit spectrum, so we have only a small piece of optical spectrum. Then we can change an angle of diffraction grating. We can take another piece of a spectrum, but the plus side is that we can change the resolution according to our task in a very big range, changing the diffraction gratings. This is the 60 centimeter size telescope, which you also saw from the video. And it is used for photometry. It has a standard photometric filters on it, and it has been used for both massive stars and host stars of exoplanets and protoplanetary disks. Smaller telescope, 30 centimeter telescope. In some sense, it is more advanced because it is newest. I mean, the control system is more advanced. You can remotely control it from computer, which is not possible with two a bit bigger telescopes. So it's very convenient to observe. You just sit on at home or even in your bed, and you can run this telescope. But currently we have a big project running while upgrading our observing facilities. And from point of view of observer, now you are supposed to sit under the dome in the observer's room. Okay, you manipulate the computer. You are not moving the telescope, but still you have to be physically there. And after this upgrade, it will be fully remote control. This is our big telescope. And also, instead of single slit spectrograph, we will have a shell spectrograph, and the one which will not move together with the telescope, but it will be fiber fed in a well fixed and stable room. And also, we will attach a photometer to this telescope. There will be mirror switching between photometric and spectroscopic modes. So for processes which are not very fast, it is basically like almost simultaneous observations. So what we do, that was about what we have and what we do. We have three main directions at the moment. Traditionally, we have for many years studied variability and evolution of massive stars, and this has a connection with this POEMS project. So I'm here within a framework of this POEMS project. POEMS means physics of extreme massive stars, not writing poems about stars. And the new direction of research, which we only started to introduce in a couple of recent years, it is a study of stars with exoplanets and protoplanetary disks. And we have been contributing to the Ariel space mission. I will tell a little bit about what it is. And from the 1st of January this year, we started a new EXOHOST project about spectroscopical characterization of these host stars. And I already told you about our plans and what we are doing to upgrade our observing facilities. So that is also, we received some European money. So basically all the money comes from the European funds, if you look at this picture. So about POEMS project, what we do, it is about studying extreme massive stars. There is some vague definition what it is a massive star, but it is mostly the ones which have about 8 to 10 solar masses. They're called massive stars. And if you look at this Hertzsprung-Russell diagram, so they are in this top area in the diagram. So this this picture illustrates schematically how the stellar evolution is going on, and for massive stars it is pretty much different from the low mass stars. These are these type of stars which end in the supernova explosion, and they die in supernova explosion and form a black hole or neutron stars. So this is kind of the difference between like low mass stars and more massive stars. The border. So if we look at this, about the physics of extreme massive stars, actually it means not extremely massive, but massive stars in extreme stages of their evolution. So after the burning the hydrogen on the main sequence, it starts so-called post-main sequence evolution, which in case of massive stars is very, very violent. So in the sense that they are going through the huge mass loss, explosions, strong winds, and so on. So and these stages are very much not so well understood in the sense of stellar evolution. There are many questions how the evolution is going on in these extreme stages. So within this project we try to answer several questions concerning that. For example, if we observe massive stars, so this is the top part of this Hertzsprung-Russell diagram. So these are very, very luminous stars. So many orders of magnitude more luminous than Sun. They are also very hot. The sun temperature is something like 6,000 something. So these are much hotter. But there are some stars which are about with a temperature like solar temperature, but many times more luminous. And many types of stars. And the problem is that we actually don't know how these different types of stars are evolutionarily connected to each other. So there are nice theoretical tracks which are calculated, but the thing is that even, for example, if you look at the star which started its life with 25 solar masses, first it burns the hydrogen staying in the main sequence, but then it makes loops. So the first it evolves to the red to becoming like cooler, but after that it becomes again hotter. And the more massive the star is, the more loops it makes like this. And understand how these loops connect different type of a star, it is astronomers do not know that. So we try to understand how different type of these massive stars evolve, which could be evolutionary changes between them, how to distinguish between a star which goes to the red and the star which goes back to the bluer side. So let's take a look at this lower part of this diagram, and here are some very peculiar stars which are called yellow hypergiants. Currently, in our galaxy, there may be only 10 of them, or maybe a dozen. So they are very rare because they are of huge luminosity. And another thing is, actually, these 2 points mean that during the time when the star was observed, maybe during last 50 to maximum 100 years, its temperature changed drastically. So something very interesting is going on with the stars. And there is an area, I painted it yellow, it is called yellow void. Yellow because this temperature, these are these yellow stars, they have the temperature around 6 to maybe 8,000 Kelvin. And why void? Void is because if you put all the stars, which we know, to Hertzsprung-Russell diagram, there will be an area where only few stars are. It looks like a void. And the reason is actually from, and these stars are very unstable. They are having big explosions, big mass loss, and it turns out that there are two things. The atmospheres of these stars, models do not work for these atmospheres. They are very unstable, so unstable that the models do not converge for them. Another thing is that evolutionary calculations show that they are evolving extremely fast. If they're evolving through some area very, very fast, it is clear that you will not find many objects in this area. That's why it is a void. But there is another peculiar type of massive stars, which are called B bracket E supergiant. Bracket E means that there are E is for emission lines in the spectrum, and bracket is for forbidden emission lines in the spectrum. And these are stars with very, very massive disks around them. It is not quite clear how these massive disks form. And there is a hypothesis that it could be that in this very unstable area, when the stars evolve from red to blue, when they cross this area, they expel a lot of material which is more or less like not spherical but close. And when they evolve to blue, this material start to concentrate more to equatorial plane, making these very big, massive dust disks which have been directly imaged. So it is not that we only conclude from spectra that they have been imaged. So there are indeed big, massive disks around this star. So one star which we have observed quite a lot in Estonia, it is yellow hypergiant V509 Cassiopeia. And there's something strange happened to this star in 80s to 90s. Its temperature changed from 5 to 8,000 in just human lifetime. It is something very unusual. And after that, it is stabilized. Actually, these are not like error fluctuations. The error bar here is smaller than this dot. So there are real temperature fluctuations which are happening in this star. And we think that now this star, it became hotter, so it became bluer. So it is kind of passing through this yellow void to the blue side. And what we see when we look at the spectra, there are in the spectra, in the shape of spectral lines, we see signatures of some kind of disk forming around the star. So it could really be, so it will become more blue, maybe it will become this B bracket E star. The thing is that these stars are pulsating, so this blue and red that indicates the pulsation. So the absorption line, blue and red, it is moving due to pulsation, the Doppler effect that the surface of the star is moving. But there is this emission part which originates from the disk, and another in the forbidden calcium line, we actually see the shape of the line, which is very, very characteristic for Keplerian rotating disks. So we think that in this star, when it becomes hotter, we see a formation of a disk. Another type of massive stars which we study is blue or these B-type supergiant stars, which are very, very hot and luminous, and they are also interesting in the sense that they are very variable. So it is not a stable star which is the same all the time, but we see a variability in many time scales, starting from minutes to months and years. And we study these stars mostly via monitoring their variability in both photometry and spectroscopy. And during my visit here, as I mentioned, we are observers from Estonia, came to theoretician in Chile to see what the theoretical models could tell us about blue supergiant star Rho Leonis, which we have been extensively observed, particularly Vitaly has observed it many nights during several years already. And it is a very massive star, almost 30 solar masses, and also I think it's here should be radius, not M, but okay, sorry. And here Ignacio has calculated a grid of stellar atmosphere and wind models, which we can fit our observations and these models to get information about this star. And this grid of models, it covers, there is a web page, I did not put the, well, anyway, Ignacio can tell you the web page. So you can choose what type of temperature or gravity, what type of star you choose here, and you can see then the theoretical spectral line profiles which you can compare to the observations. And for example, for this Rho Leonis, we worked together. Ignacio ran many different parameters, code with the different parameters, and we found that the best fit parameters for this star will be this 23,000 Kelvin and log G 2.6. It means that it is a supergiant star with a very extended and rarefied atmosphere. And the interesting thing is that we can now disentangle the radiation which comes from the stellar atmosphere and what forms in the wind, because the wind of this star appears to be not only very variable but highly unsymmetric. So modeling unsymmetric wind, it is something which is too complicated for nowadays computer capabilities. So this now this project, the POEMS project, it unites 10 different institutions in Europe and mostly in South America, but also one from Azerbaijan. So we collect different types of observing data and compare to theoretical models, and want to learn more about how massive stars evolve and what are the different stages and evolutionary connections, internal structure, and so on. So yeah, this is a slide which shows what different types of things about the massive stars we study. So now about the new project which we started about host stars of exoplanet and protoplanetary disks. And of course, the motivation for this is this so-called exoplanetary revolution. So this graph shows how fast the number of exoplanets goes. So we are moving from a stage, oh, see, there is an exoplanet, to the question, how it looks like, what it is composition, how it formed. So from the finding a planet to a characterizing a planet. So in this sense, it is a very interesting time in this area. I still remember very well when there was the first conferences where someone found an exoplanet, and it was a very, very big deal. Now they are coming already in thousands. But most of the interest usually goes to the study of exoplanets themselves, and people mostly neglect the host star. Although from my point of view it is strange. How can you study a planet if you know nothing about the host star? So my understanding, it is not possible. Even because when you observe, you don't usually, there are these direct images of exoplanets, there are just maybe 10 of them, no more. So everything which is, what we know now about exoplanets, it's about observation of the host star. So we think that it is really important to study the properties of the host star and the connection with the properties of the planets and protoplanetary disks, and how the planetary formation affects and how we get so many different planetary systems which are anything but not like a solar system. So most of the systems which we know now, they are very different. And it is also a big challenge for planetary formation theories, because, well, up to now they were like tuned to explain the solar system, and now it turns out that the solar system may be something very unique, and planetary formation theories need to explain all the big variety which is observed now. So, well, I will not read this, you can read it without my help. But there are like the two directions about our project, and it is a new project. As I said, we only started this year, and it is based on our expertise in stellar spectroscopy. And also in the possibility to use our observational facilities, which are getting much better by the end of this year already. And so we study the stars and with planets and protoplanetary disks. And this activity also goes some input to the European Space Agency, ESA, not ESO, like here in Chile, but ESA, with the Space Telescope Ariel. So we are contributing for preparing to the Ariel, and this is also a consortium work, but the consortium is much smaller. As I said, the POEMS consortium is 10 institutes, so here we have only 4 institutes. About the Ariel space mission, it is a space telescope which will study properties of 1,000 planets. So this is the first time when there is a big like representative study of different type of planets will be carried out. So it will be possible, and the reference sample, the sample of the object for this, it includes very different types of stars and very different types of the planets. So they try to get information about as many or as possible different types of stars and planets to understand the planetary formation mechanism much better. And there are two actually spectrographs which will be on the board of this space telescope. Currently it is planned to launch it in 2029, so and to my understanding it is pretty much well on time. So they say that it is always delayed with the space telescopes, and so my hope it may be that it won't be delayed. And well, it takes a spectrum of a star and the spectrum of, there is also a small, it's not that important to see this video, but the thing is that when the planet goes over the stellar disk, so the light from the star goes through the atmosphere of a planet, and then you have a spectrum. You need to disentangle the stellar spectrum and the spectrum from the planetary atmosphere. So it's quite obvious that you need to know the properties of the host star very well to subtract it from the planetary signal. And another thing is that with a very tight time schedule, you need to know the exact times of the transit very well. So we, in Tartu, we contribute to the two scientific working group of this mission. One is the stellar characterization, so trying to get as good as possible parameters and characteristics of this host star. And another aspect is the ephemerids working group. The ephemerids, it is well, exact timing and when the exoplanet passes. So to determine the good timetable for aerial observations. So this is a preparation for aerial observations. And we are also preparing to contribute to planet formation working group, but it is more about when the aerial will start produce results. So now we give our input to the consortium, and when the aerial will start produce results about the planets, we will have a right to use them. Okay, so now, yeah, that was the last slide, how to become an astronomer in Estonia, because you know, there were a lot of people, young people, the students. So, taking into account how small Estonia is, just 1.3 million inhabitants, so they are not, people who want to become an astronomer start a bachelor studies in physics, chemistry and material science. So the future chemists, physicists and material scientists, they are all in the same pot for the first 3 years. And only after that you specialize to physics with some astrophysics modular. You can have a supervisor from our observatory, and on the PhD level we have our own PhD program in space research and technology. But I think that's it. Oh yeah, about number of people. So, thank you. Whew.
Thanks, Anna. So now we have time for some questions. Anyone?
Okay. I would like to ask a question about you showed us a non-trivial behavior of the massive star, which have a change of its temperature like a roof. The temperature change to the high temperature and then
No, it goes to the low temperature. Red is low actually temperature,
yes.
and blue is hot, and then it goes back to the hot. But there is a thing that there are, let's say, many types of fuel inside of the star, right? So if the star is massive enough, it can ignite more heavy elements. So in the low massive star, you have your hydrogen burned, and then basically you can have your helium burned, but not even for low mass star, no. But in more massive star, after you burn your hydrogen, you burn your helium, you can start burning more heavy elements. And every time when it ignites to the next step of this fusion ignites, the star becomes hotter. So it goes to hot again, but then it is kind of burns out, goes to the head. So it is like that, more or less. Yeah.
So for less massive star like sun, there is no such behavior.
No, because they, you know, when you don't have, what is usually, there is a gravity which contracts the star, and there is this pressure of radiation which expands it. So the star is a balance of these two, like basically, right? So when the fuel is less, the star starts contract, but if you know the contracting, it usually heats up.
Yeah.
So if it contracts violently enough, it heats up enough to ignite the next level of burning. But if it is not very massive, then it will not heat up enough in this process to start burning the next stages. So sun will not start burning anything heavier. But a massive star, they say it is like an onion structure, because there are many layers in the star which are burning different elements already.
Different type of nuclear reaction.
Yes, different type of fusion reactions, yes. Until it burns to the iron. And then you have this iron core, which is growing, and at some moment it collapses and you have a supernova.
Yeah. So can we say that the more massive star is,
Mm-hmm.
the more complicated its evolution are?
Yes, it is. That's why it is so exciting to study them.
So more, is there any actual boundary limit for the massive star?
There is, but the thing is that it is strange that some stars are more massive than the theoretical predictions for them. So there is a big mystery how they can exist, because from the theory point of view they cannot. Yeah, it is not possible. The radiation will be too much to hold them together. They are supposed to blow up immediately, like they cannot even form. So yes, in massive stars, or the formation of massive stars, this is something which we do not study within this POEMS project or in our observatory, but it's also many questions how they can form. Yeah.
Another question?
Do you know how many years the process takes to be increase the temperature or low temperature to increase the temperature? How many years pass?
Millions. I am not so good in the time scale, but not in a human lifetime scale. In that sense, these yellow hypergiant stars which I mentioned, they are very, very unique. You can, but there are still discussions. Some astrophysicists believe that we indeed, in the time scale of 100 years, can see some signs of evolution. But other people think that no, we only see changes in the outer layers. The stellar evolution itself is still very slow, like in the middle of it.
Okay, but how you can say that you have that behavior? Because if you say that you could take 1 million years, how you know that that process is in the star?
Well, if we model a star, like we model a star, we know how much radiation goes. Well, the nuclear processes produce that and that amount of radiation. There is a gravity which holds it together, and we know that the star is supposed to get hotter.
It's a model.
Models.
It's a model.
Definitely, it is a models. It is a models, and the thing is also that the models for massive stars, they are extremely sensitive to the amount of mass which is lost during the evolution. So if you lose more mass, then the parts could be different. But the general understanding is that they, as I showed, that they go to the red, then they go to the blue, they explode as a supernova. This is a like, very general picture, and people are not, generally believe that it is indeed so. But there are many interesting things. There was a supernova, I was a student then, 1987, when a blue star exploded as a supernova. It was a very big surprise for everyone because it was generally believed that they cannot. This type of star, because it was known, the progenitor of this supernova, it was known. So what star it was, and as a result of that, the theories of stellar evolution for massive stars were like revisioned and changed quite a lot. So there are many unexplained things. So yeah, we can say that yeah, the theoretical track should be like that, but as I showed this big zoo of the. Yeah, you can put some theoretical curves on it, but you cannot be 100% sure.
Okay.
More questions? No? Maybe I have one. How many clear nights do you have in Tartu through the year?
I can tell you statistics of observing nights. I mean, I think that for the last 10 years, the peak was in 2014 when we had 90 observing nights. And the lowest, of course, well, this year we will have a very little number of observing nights because we had a re-aluminization of our mirrors. So the mirrors were taken out from the telescope, sent to Germany. They had got new coating, the reflecting coating, and when we put them back, so for quite many months we did not observe. But the average over the many years, it is 50 observed nights.
And usually that night are in the summer, right?
Sorry?
The clearest night are in summer? Or?
No. The best observing time is actually now. So they are spring and autumn. And during the winter we don't have so many clear nights, but the night is something like 16 hours. So you can start observing something like 4 p.m. in the evening, and you go the whole way until the morning, like 10 o'clock. One Vitaly knows very well. Yeah. And then we try to split the night between two observers, having like 8 and 8 hours because it's too hard. But in contrast, in summer, the nights are very short. So with bright stars, spectroscopy of bright star, it is like up to 4 hours, but only bright objects because the contrast with the sky is not so much. But spring and autumn, we have many clear nights, and the length of night is something reasonable, something like 10 hours. So, yeah. March, April, beginning of May, and then end of August, September, beginning of October. Best times.
More questions? No? So let's say again to Nana.
you for your attention. I hope it wasn't very boring.